Okay. Thank you, Stephanie, for the invitation to this seminar. Welcome to the participants. I will present something about our standard for thermal energy storage. First, I want to present some facts about the VDI. We founded in 1856, have 130,000 members, and 10,000 volunteers works in our standardization work committees. We have 600 committees and 12 professional societies, and yes, 46 regional associations. But the main topic today is the standardization and the VDI setting the technical standards. We have, as I mentioned before, over 600 committees, and this develops recommendations for actions and other publications such as studies. The main product, the VDI standards, including international recognition, and we also organize some expert forums or workshops with our 10,000 voluntary experts. And at the moment in the VDI, we have 2,200 applicable standards. Now I start with my main topic about the standard for thermal energy storage. It's the focus is on the VDI 4657 Part 2, Planning and Integration of Energy Storage Systems in Energy Building Systems, thermal energy storage. The draft of the standard will be published in January 25. But we get the first questions about the standard before it is published now. Therefore, I will explain the scope of the standard. The scope is intended as an aid of manufacturers and building services planners for the dimensioning of storage tanks for sensible and latent heat. And in addition, the hydraulic system integration of thermal energy storage systems of different designs and usage requirements in buildings is described in the standard. And there are some typical applications. First, the storage of heating, cooling energy to decouple generation and demand for bridging breaks in the supply or consumption of energy and energy management when using several heat and cooling generators. These are also elements of a future very flexible requirements of the energy systems and especially the building energy systems. It shifts loads, hourly or daily loads and seasonal loads, the energy management to increase the building's own use of electricity or for grid reactivity control. And the last but not least, it's the typical application is reduce the cycle frequency and increasing the running time during a cycle of heat and cooling generators in the case of only partial load. Okay, we have a series of 4657 standards. Therefore, the thermal storage standard is part 2. Part 1 is under development, and we expect the publication in 26. Is the basic standard about design and integration of energy storages in buildings. And part 3 was published in August 23 with the focus to electrical storage applications. But now we speak about thermal energy storage. In addition to fulfilling additional requirements, those of system hydraulics, thermal storage systems are primarily used to balance the differences in output and time between generation and demand. Thermal storage tanks therefore play an important role in load management, but their effect cannot be targeted. In building services, engineering, the building masses and the distribution systems also act indirectly as thermal stores. I think all of the participants know these effects, but their effect cannot be targeted. Therefore, it was important, or it is important, in order to meet the specified requirements for select and dimension of energy storage systems in the specific building. It is very important to choose the storage technology and design, to decide to organize the right load management, to integrate into the system technology, and the storage size is very important. And that was all these points was the motivation for the development of VDI 4657 to describe the planning process for selection and dimensioning of storage tanks for sensible and latent heat can be carried out. Heating and cooling applications were considered equally in this standard. This means that the selection logic moves away from liters of water content to kilowatt hours of heat content, the energy of the heat content and not the liter, because only the heat content is important when selecting a storage tank. In this way, storage tanks for sensible and latent heat can be selected equally, and the selection is determined by the boundary conditions of the application. In the end, it wasn't so simple after all. A research project was needed to determine the correlation between operation and heat content. And the end of this main result of this research project was the standard 4657 part 2. In the project, an easily determinable correlation was found between loading capacity, achievable or usable relative heat content, and the temperature difference at the producer or consumer. The procedure for planning and storage selection is described in this draft of the standard. And the final result of all this, of the research project, is the diagram which you see here on the slide, which shows that the relationship mentioned for a storage tank under consideration. Here's shown the diagram for a heat water storage tank for this 400 liter capacity, indirectly loaded via heat exchanger and direct discharge. And the VDI 4657 part 2 describes how a storage manufacturer can proceed in order to determine the measured values for creating a diagram similar to this one, with just a few measurements. Here you see an example for the procedure for the warm water storage tank is as follows. Only the lower part of the diagram is now visible. The values of the standardized heat content can now be read off depending on the loading volume flow. They are the individual loading volume flows for 200, 400, and 800 liter per hour with different values for the heat content. The correlation between loading volume, flow, and achievable heat content is recognizable and significant. This was a very important result of this project. And similar, the upper part of a diagram can be used to determine the relationship between the temperature difference at the heat exchanger and the relative heat content. And here you see, depending on the loading volume flow, the values for the relative temperature difference at the heat exchanger can now be read off the standardized heat content. They are for the individual loading volume flows. And here is the relationship to Kelvin per Kelvin. The relationship between the temperature difference at the heat exchanger and the achievable heat content and vice versa is also recognizable and significant. And now I show my last slide. It is planned a follow-up project for the applicability and scalability, among other things, will be investigated in collaboration with storage manufacturers, and we plan to bring these results to the 3820 part 20 as technical standards, which has long been established, in which the product data for software programs is described as machine readable. And the embedding of the findings from the research project and 4657 part 2 must be driven forward so that the procedure described is incorporated into the planning process. And of course, we also plan the includes the usability in electronic data exchange and for comparison in building information modeling. I hope you understood the results of this research project and the results concerning the draft standard we will publish in 25. Thank you very much.
Okay, thank you very much. So I think you gave a good overview of what happened, and especially what are the results. I know that a lot of work went into getting there. So
also we'll see that AE was involved.
Yeah, so it was a lot of work there. Is there any question from the audience? So feel free to ask or directly or in the chat. Maybe I ask in the meantime, do you, because I really don't know, is the VDI paper, which is planned to be available from next month on, will it also be available in English or is it German only?
No, at the moment the draft will be only in German. And the end product will be in both languages published in 26.
Okay, so it's a little bit to wait, but also in 2 languages. Perfect. Okay, so again in the audience, is any question? Sure, Steve, please.
Yeah, so thank you for that presentation. It's really great to see the development that is going on. So you showed an example which was for a sensible heat storage, I believe. What is the status of the standard with regard to latent, for example, latent heat storage? Is that covered at this point in the current standard?
You mean the latent?
Yes.
Yeah.
So phase change.
I think it's covered.
Okay.
Yeah.
Okay.
As I understood my experts from the standard committee.
Okay. Well,
right. Okay.
I'll look forward to that. I may have to wait till the translation comes out, but I can read certain portions of it, so I'll look forward to that. Thank you.
Yeah.
Okay, thank you. We have now one more question in the chat. I just read it, so it's on record. Geoffrey is asking, I would like to know how high the investigation went in terms of volume for the sensible thermal energy storages. Does it stop at 800 liters? Now, what was, if I understand right, maybe the maximum storage capacity in terms of volume?
I think in the project was the maximum capacity were 800 liters. That means I don't know if it was not investigated more than 800 liters, if I understood it right. The right at moment the final report of this project, and I will have a look in it.
Yeah. I just wanted also to say that it will be in German as well, unfortunately, but maybe the graphs are able to understand. So there will be a final report for the project.
Yeah.
So Geoffrey, I'm happy to send you also the name of the project later, or the link, maybe when it's due to hand in. Hendrik Wust, please.
Yeah. Hello. Thank you for your presentation, Mr. Theloke. So I think I had the same question for the final report of the research project. I'm especially interested to know what the project, what's the name, and what the content of the project is. Maybe the further Kennzeichen also. So I think it is enough to get it in later.
In work, progress on work at moment, and we must deliver this final report at the end of this month. Yeah, and then it is published also.
Thank you.
And Stephanie Tafelmeier will give a link to the VK test. Yes.
Yes. So I was just looking. I couldn't find it on the VK test. So VK test is the name. I couldn't find it on the Enargus system. If unfortunately it's not listed there, I need to check again. It's a bit too quick now. If I would have entered in the chat, but the name of the so this is the name of the short version. Maybe I can have a quick sneak during the next presentation, and I can give you also in the chat the further Kennzeichen. Okay, so the last question, and then we will start with the second speaker. But one question in the chat is now: are there any kind of similar standards such as ISO or other international standards?
We are in exchange with the Canadian radar. You was shown in the picture at the moment. We are in some started the exchange concerning ISO activities, and I think Reda Cheber can explain it better to you.
Hello, do you hear me?
Yes. It sounds
Yeah, so this is
I hear you, yes.
Okay, I think I hear an echo. I apologize for that. Maybe I joined in two ways. Okay, yeah, so for the ISO, we will discuss how we could kickstart that in the next couple of years. It takes time to implement that. Thank you. Back to you.
Thank you. Okay. So with this, I would move forward, Steve, to your presentation. Feel free to share the screen. Yes.
All right. So hopefully that is working now, and we can get going. Well, thank you for the opportunity to present the information that we are working on. As you can see, the title of my talk today is on uniform ratings and performance estimates for packaged PCM thermal storage. Before I start, I want to acknowledge members of the team and really acknowledge their contribution, and that's Keith Nugent, Phoebe Chambers, Ross Breton from QSBRI, and note that this study is conducted and in collaboration with CanMet Energy and under Natural Resources Canada. And this activity is under the direction of Dr. Reda Jabbar, who we just heard from. So moving along. So this presentation is going to be a little bit mathematical, and I would like to point out that we're not as far ahead as our German colleagues in terms of publishing a standard, and we're still working on the development of that, and that's what I'm going to talk about. In North America, we're starting to see a number of commercial products being introduced into the market. These products range from sensible heat storages to latent heat storages. And as a result, that has motivated Natural Resources Canada to evaluate test methods for rating and predicting their performance in the field. We at QSBRI Innovations were commissioned to do some basic introductory work in this area. And the results of this work are intended to inform the newly formed Canadian Standards Association, CSA, Technical Subcommittee number TC444 on energy storage equipment and systems. And that committee will be in operation over the next couple of years. So as I said, this presentation focuses on packaged latent heat thermal storage systems that are using phase change materials. Most of the members of the audience probably know this, but there is a strong move, certainly in North America and around the world, to reduce fossil fuel use. And this is creating concerns for utilities in terms of their capacity to meet peak electrical demands. We also have the advent of renewable energy sources, which can be intermittent at times. The utilities are realizing now that space heating and hot water heating and cooling represents a significant load on the utilities. And by utilizing load shifting of thermal loads to off-peak periods, it's possible to lower generation costs, as shown in these graphs. So why PCMs? So the advantage of phase change materials are that they do offer a high energy density storage. When they're properly insulated, or I should say well insulated, they can store thermal energy for reasonably long periods. You also can tune PCMs to deliver heat at a desired temperature. And some PCM materials can be inexpensive. So what are the challenges with PCM storages? What are we trying to achieve? They've got to operate reliably. There has to be efficient methods to add and remove the heat from the storage, effectively efficient or effective heat exchangers. We know that certain PCMs undergo a volume change with temperature, and this can compromise heat transfer. A term called phase segregation can occur in certain cases where you have the different components of a PCM separated over time, affecting the performance. And a key point and the focus of this talk is that assembled PCM storage units will likely not perform directly as would a small sample on a PCM material. The challenge for us in trying to characterize the performance and the operation of a phase change material during heating is that the process is highly nonlinear, as shown in this diagram to the right. Phase change materials, as I think we all know, go from a solid to a melting or process and then to a liquid state. So the objectives of this study is to identify standard test methods and equipment that can be used to experimentally evaluate packaged PCM storage units. Also to arrive at methodologies for rating the thermal performance, including things like thermal capacity, charge and discharge rates, standby losses, round trip efficiency, etc. So as well, we want to evaluate the suitability of the proposed test methods by doing actual tests on commercially available storage units. And hopefully from this, we can develop a uniform performance characteristic or equation, which the coefficients from the test can be used to determine the performance. And this is executed by using what we call a black box testing method, where all the measurements are conducted outside of the storage unit itself. Finally, we want to develop this generalized model of phase change thermal storage. So it can be implemented in various system simulation programs, most notably Transys, which is used in North America. So the approach can be summarized by this diagram. So what we have on the left-hand side is we have a standard test method where we conduct a black box test on a thermal storage. We get test results from that test, which produce raw data. That raw data that can then go into the product ratings, things like capacity during charge and discharge, round trip efficiency, etc. But that raw data as well can be used in a regression analysis. And if we have a generic performance equation, then during the regression analysis, we can derive coefficients which describe the heating and cooling process and the capacity of the thermal storage. Now, if we use that generic performance equation, we can also implement that in a simulation program, which allows us to use site-specific load data to predict how systems would perform under different loads and different scenarios. The challenge then really comes down to is can you come up with a generic performance equation which is flexible and suitable for this application? So this is the testing portion. We decided to use an existing standard published by ASHRAE, and it's titled Method of Testing Active Latent Heat Storage Devices Based on Thermal Performance. It's a non-intrusive black box test, and this standard was actually withdrawn a number of years ago, but there's a lot of interest in re-implementing this standard, and there's a series of standards related to this. And we conducted testing on a number of PCM storage systems commercially available to this standard to obtain data. And effectively, that's shown here, the type of scenario. So we have the sample. We measure the inlet fluid temperature, the mass flow rate going into the standard or into the storage, and we record the outlet temperature. The diagram in the bottom, which is a little unclear, is actually directly out of the standard. And the type of data you get out is shown on the right-hand side during a charging phase, or on the left-hand side of the graph is the charging phase, on the right-hand side the discharging, and there's a standby period in between to determine the rate of heat loss from the storage. These are what actual test results look like, and there's a number of lines on this curve. The most notable ones are on the left-hand side are if you can see the color of the green and the orange lines, which represent the inlets and outlet temperatures during the charge process using the left-hand axis. On the discharge, you can see the orange horizontal line, which is the inlet temperature, and the gray line, which is the outlet temperature, which drops, and you can see the phase change portion of the curve, and as the discharge continues, the inlet and outlet temperatures coincide. So in developing the performance equation, we looked at a number of other types of developments, and we gained some inspiration from what's used to characterize solar thermal collectors. And those are of you that are familiar with the so-called Hodel-Willier-Bliss equation, which is shown below. What you have is a equation which allows you to determine the outlet power from a solar collector as a function of number of terms representing the optical performance, the heat loss coefficient. And there is a factor, FR or F prime, depending on whether you're using inlet or mean fluid temperature, which relates to the heat removal factor from the collector, which is a function of the flow rate. And that is integrated to determine the energy produced from the collector. So there is a PCM storage equation that was put forward by Lane, which really covers the sensible heating portions and the latent heat portions of the process. Actual test data is shown here on the left-hand side. This is the energy stored versus the temperature during a charge process. And what you see is the inlet temperature and the outlet temperature and the mean temperature, the average of those on the left-hand side. Now, what we wanted to do was try to develop a universal characteristic to minimize the amount of testing required. And so we conducted various tests, in this case, charge tests, using different power inputs. And so you see what's shown are tests at 6 kilowatts of power input to the storage and at different liquid flow rates flowing through the unit. And what we see is that if we plot this against the inlet temperature of the fluid, we get a series of curves. Each curve is unique and they don't collapse. So looking at this is not a universal characteristic, and so we wanted to see if we could go further with that. So what you have in this graph, you can see that we ended up representing the data on a plot of energy storage versus outlet temperature. And we can see that the curves are actually collapsing, which is very encouraging in terms of arriving at a generalized performance representation. And if we look at this, although things collapse very nicely, this curve is based on outlet temperature. And in a simulation modeling process, you are most likely going to know what the inlet temperature is to the thermal storage and the power level and the temperature of the fluid. So it's less functional if you plot this again against outlet temperature. And we have an algorithm that we can derive back the inlet temperature, but it's certainly not as convenient. So we look to other possibilities. And one of them, once again, was to plot it against the inlet temperature, as I showed. That wasn't too encouraging. So what we did is we looked at introducing a flow factor similar to that FR value, which I mentioned with regard to solar collectors. And instead of using inlet or outlet temperature or mean temperature, we introduced the term T star, which is an effective temperature for the storage. And you can derive this from these relationships shown here during the charge and discharge processes. And the points of interest is this F sub F, which is the so-called flow factor, which allows us to collapse the data. Now, from the test data, you can arrive at this corrected temperature versus the power level divided by the flow rate. And when we do that, we see that in these cases, we get an effectively linear relationship. And the slope of that curve is the flow factor as shown here. And so those are two different cases shown in those graphs. So when we apply this and we plot this against this corrected effective temperature, you can see that we're back to a case where we've been able to collapse the performance on a unique performance characteristic. Now, the challenge then is, how do we come up with a relationship which represents that very nonlinear expression? And this looks a little complicated, and I have to give credit to my co-authors who worked on this. In effect, what we have is three segments. One which represents the sensible heat portion on the left-hand side, and then the portion where you have the phase change in the center, and then you have the liquid phase, which is on the far right. So this equation has a number of terms in it. In actual fact, it has, as we're seeing there, 7 terms, which have to be derived from the test results. And so how do we do that? Well, I'll get to that in a second. In effect, if we do fit the data, we see that we get slightly different curves for charge and discharge, as you would expect, because the heat transfer processes are operating in opposite directions. So this is the algorithm that we use. It's quite simple and quite straightforward to allow us to determine the state of charge. And in the sake of time, I'll move on. When we do use this algorithm and fit it to the data, what we can see is this is a comparison of our experimental data versus the predicted values based on the algorithm. And you can see this looks very good in these 3 cases. There's a little bit of ripple down on the bottom curve related to the experimental data at that time. So this is very encouraging. And that was a charge, and this is a discharge test. And once again, the data looks very close. So what we've done is that we've created a template within Microsoft Excel, which allows you to input your test data, and using the analysis package, which exists in Microsoft Excel, you can perform a regression, and it will produce the coefficients that you need for the curve fit, including the flow factor and these various terms which form the equation. And what you can see on the graph below is the data that is the curve fit to the experimental data, and you can see that the results look quite good. Now, what we've also done is, moving forward, we've looked at trying to implement this relationship using the regression analysis and that generic performance equation during the test and the analysis of the results. Once again, we derive these coefficients. Within the simulation program is a component, or in relationship to transits, it's referred to as a type. And so what we have is a component which represents a PCM storage. It contains the generic performance equation, which you can see, or I've previously gone into. And with the derived coefficients for the particular product, we are able to use those in the simulation and produce the results. And this is just an example of that transit type. And you can see that on the left-hand side, these are the inputs. There are outputs which are not shown. If you scroll down in the type, you'll see them. But those coefficients are entered. And in effect, what the simulation will do is produce a similar type of performance characteristic. And with that, you can also output the energy, the state of charge of the storage. And so this is a charge process. The blue line represents the temperature of the fluid going into the thermal storage, and the green is the outlet temperature. And you can see the charge process continues until those 2 lines converge. at which point the storage is fully charged. Similar discharge curve is shown here. And what you have, once again, is the blue line is the temperature of the fluid going in, and the green line is the outlet temperature. And once again, the lines converge. Okay, so just for fun, we decided to put in water to see what the equation would do. And certainly water is not a phase change material at the temperature we were looking at. And we were very pleased to see that the correlation equation came out linear and that the results are consistent with what we would expect. Okay, so in conclusion, so what we've shown is that it's possible to characterize a PCM storage, and we can do that from a non-intrusive black box test where we don't have to go into the storage, which is important as many manufacturers of products don't want to divulge the characteristics of their specific PCM or to tell you about the details of their heat transfer components. What we can do is that we've been able to use this effective storage temperature to allow us to collapse various performance conditions onto a single characteristic. And we've been able to implement that into a typical design simulation program. As I said, in this case, the transit routine. So we still have work to do before this really goes into use, and that is we need to test other PCM formulations. We must do more testing and analysis on different storage sizes and storages with different design features. And ultimately, we need field data to compare with the simulation results as well. So thank you for your attention, and any questions, I'm happy to give you my best attempt to answer them. So thank you. I'll stop there.
Thank you very much. Thanks. It's a very, very nice approach, I think. I would have a couple of questions, but I, of course, let the audience first. So we have at least one in the chat, which also from Geoffrey. It says, is the Transys model respectively type available? If yes, is it open source? And where can it be found?
Okay, so the Transys type is in testing right now. It is a deliverable to Natural Resources Canada, and they will be doing a series of evaluation and checks on it. And in effect, it's up to Natural Resources Canada when they feel it's appropriate to release this Transys type. It will hopefully go into the standard grouping of Transys types, which is available through Transys or more than likely available through Natural Resources Canada. So yes, that's our status. This information will be fed to the CSA Standards Committee, and they will deliberate on the processes which we have put forward. So I hope that answers that question as well.
He says thanks, so I hope so.
Okay.
The next question is from Harald, please.
Do you hear me?
Yes, I do. Thank you.
Okay, perfect. It's not a question, actually a comment. There is a group in Belgium which works on the same problem.
Yes.
And they have an approach that they call charge time energy fraction method. Do you know about it?
I've sat in on a number of presentations on the IEA task, which is working on phase change storage. I'm not sure if I'm familiar with that exact process. We are trying to capture as much information as we can on different approaches and different standards. For example, the new German standard, and so we're hoping to really collaborate with groups, and we'd like to arrive at a uniform process and standard for this and representation. My understanding is that as the CSA goes forward, that they will be putting forward a bilateral standard with hopefully with the US, with ANSI, and certainly further collaboration with the EU and other groups is very desirable. So hopefully that will happen. And thank you for that recommendation. We will certainly follow up on that as well. So thank you.
I have one information for you, because they gave a presentation, I think 2 years ago at a conference in Spain.
Yes.
And they had a very simple formula that gives incredibly good results. And I was completely shocked, because I work now 25
Yes.
I work now 25 years on phase change materials, and we had all these complex fluid dynamics and finite difference methods.
Yes.
And I couldn't understand why, with a simple formula, they get as good results for different discharge rates and so on. So I talked to the guy who gave the presentation, and he gave me some papers. And after a few weeks, I had an idea why it works. And the reason why I'm telling you about it is because I think it's very important to understand why you can come up with a simple formula, to understand the conditions for it, and maybe get an idea when you might get off the track. And I think the reason why these simple formulas work is that when you have a storage with the heat exchanger and phase change material, that independent on how you exactly discharge it, and I'm talking the volume flow and the temperature profile, the phase change front will always move in a very similar way. So you always put cold water on discharging in on one side, and on that side, the phase front will move the fastest away. And on the outlet, when the water is already heated, it will move slower. And this curvature is typical for the heat exchanger design in the PCM that you use. And I think, let's say I'm convinced that this is the reason why for a certain design, you can come up with a simple formula and then basically calibrate it based on a few measurements.
Well, that's exciting news, and I certainly would love to see that. In actual fact, even though the equation that we present looks complex, it actually just describes three components of the heating and cooling curve. And some of the higher order terms are really just to smooth out the corners. So it's effectively a piecewise fit to the data. So it's not really as complicated as it appears. The other important point, and this has probably been addressed, is the actual test required to get that data, which you need for any process. And the similarity here is that, once again, this is a black box test. There are no thermocouples, there's no measurements being taken inside this box. And that was a criteria of the process. And that creates a few challenges, particularly because of the fact that each storage is unique in terms of capacity, and as you mentioned, in terms of heat exchanger design and phase change materials. So the test procedure, in effect, is very important as well, and trying to minimize the amount of measurements that are required to lower costs to the manufacturers and make the process uncomplicated. There's where that portion of the whole process comes into play. So thank you for pointing that out. We'll certainly look into that. And if you have those references, please send them to me. My email is on the front of the presentation, so it would be great to get as much information as we can.
Yep. I will send you something. Thank you.
Yes.
It's very interesting presentation.
Okay. Thank you very much.
Thank you. I overlooked one question before in the chat from Louis, which asked, does the generic performance equation include skin loss or gain, or is it simply handled separately?
So I assume by that term we're talking about the heat loss rate from the storage.
I think so, yes.
Yes. And I mean, that occurs during the charging process and the discharging process, but also in the standby. And the algorithm would include, and we haven't implemented this, but yet at this point, if there is a period during which the storage is not being charged or discharged, then there is heat loss or gain to the storage, depending on the conditions, and that would be dealt with by a separate loop within the algorithm. So we believe it's not going to create any issues. The particular PCM storages we tested had a very low heat loss rate, but that certainly will not be the case in all cases as well. So that's a portion that we are going to implement, and we will also compare that against, field data and test data as well. Okay.
Thank you very much. I may also would like to ask something, as there are no more questions in the chat. I was not really a lot involved in the project, which Mr. Theloke just showed before. They call it the V. Yeah, was German VK-test, never mind. But one approach was also to understand the impact if I charge my storage, no matter if sensible or latent, if I charge it with a set temperature, like saying with one fixed constant temperature from the fluid, or if I make a specific power. Because at the end, which could be an application, is to say you don't need a specific temperature, you need a specific power at your discharge. At the charge, not necessarily, but at the discharge. What was your setting for charging and discharging the fixed, like a constant temperature, constant power?
So I assume I can jump in and answer a portion of that question. So if you go back to the original ASHRAE standards, the original standard was written on charge and discharge at constant temperatures.
Okay.
The later version came out with constant power. And when you charge the storage at a constant power, you get a range of inlet temperatures. And as well, they had a constant power discharge, which is experimentally is more difficult to achieve from what we were doing. You basically have to extract a constant amount of energy from the discharge loop. The correlations we have are based on constant, well, some of them are based on constant inlet or temperature, and some are based on constant power. We've checked our results, and this seems to apply well to both cases. So that's certainly something we're going to follow up on even more rigorously. But at this point, it looks like these correlations will work for constant power charge and discharge as well as constant temperature.
Yes.
Certainly in real life, these charge and discharge are not usually at constant temperatures. They respond to the load, and that's where you get into the full-scale system simulation.
Yeah.
And as well, checking it against field data where you do see that type of variation is certainly one of the areas that we want to follow up on. Okay.
Yeah, I think one result was that it could have been shown that the I hope I say it right, that at the point when the constant power just goes down because there's just not enough. The flow rate is already at the maximum and the temperature is too cold for latent storage at a certain point. The power is not available anymore. This correlates to a certain point on when you have a constant outlet temperature of the fluid. And this was kind of interesting point to find to maybe avoid measuring the complicated way with constant power and using the constant temperature. Yes. Unfortunately, I'm not that involved in the project, and it's not published the final report. But it would be good. I would be happy to have some extra exchange on this if you like to.
No, that would be. I mean, we would love getting more input on this. There's a lot of work going on, and there is an IEA task certainly working on this. And we've been, I guess we were late arrivals to that activity. And certainly we encourage the input and feedback on what we're proposing. But I mean, you raise a good point. There is a point at which the constant temperature discharge and the constant power converge ineffectively when you've extracted all of the power. That's when you see the convergence of the temperatures as well. So no, absolutely, I would love to provide.
I'm happy to forward this because I was just not only a little bit in this group, but I don't know, maybe in the audience there's someone, or I will forward to the responsible people and also Mr. Theloke. Because I think it's a nice way to grow. And also, Harald, when you're happy to share the paper you mentioned before, just to connect everyone as it should be. Okay. So thank you very much.
Well, you're welcome, and thank you for the opportunity to present this work.